welcome everybody. We have another really special guest, and you know, there are a number of guys at on Solana and at Anza and formerly Labs that do some serious work that impact you every day in a really powerful way that you may not know who they are, and but you should. And Andrew's one of those guys. I remember the first time I actually knew who Andrew was the video he did with Jacob Creech. You remember that, Andrew? The spotlight?
Yeah, that was fun.
That was, I mean, and I was like, I got to get that guy in here somehow, some way. And then we fortunately made connection a couple of other ways, you know, nepotistically in a funny sort of way. And Andrew's been gracious enough to come today and talk to us about some cool stuff that is very current. So, you know, I already told Andrew how we roll here. We will ask very deep questions. We want to get into the weeds. So we're not going to sugarcoat or water anything down. We're just going to rip, leave everybody with some questions and learn a lot. So Andrew, the show is yours. Appreciate you being here. Oh, look at that. I love it.
So yeah, I'm just going to go over like a quick history of block production in Solana and now Agave, because when you reached out, you said this series is about really like the economic consequences of technical decisions, and I just felt like the history of the development here really highlights that. With that said, let's get into it. Block production obviously is the process of producing a block. We do this every 400 milliseconds, but I think I have maybe a different view of this than most people. As I've worked on block production for the last 3 years, or just under 3 years. And this is really like two separate tasks or responsibilities that are merged into this, you know, grouped together block production. There's packing, which is sort of selecting which transactions actually make it into the block. And then there's scheduling, which is just how can we process these transactions in a safe manner and as efficiently as possible. And in Agave, these two are tied together, partially because we're constrained by like the execution time, and this sort of gives us a feedback loop between execution and the decision on whether or not to include transactions. It's also worth noting that packing is primarily about like filtering out transactions. It's not a lot of choosing this is like the best transaction. We just sort of filter things out and then go in some order after that point. And yeah, as Linus once said, scheduling is easy. So, and I think that's mostly right here. Once we've determined which transactions we actually want, there are just some rules that we need to follow. We just can't execute things that conflict with each other. By conflict, I mean, you don't have like two transactions writing the same account on separate threads. They could go in the same thread back to back, but they just can't go in separate threads. And then similarly, if you're reading, it's a little bit tricky here because the resources that we touch, the accounts, aren't statically declared on the accounts, on the transactions. If there are address lookup tables, then we need to like just resolve those before we can begin like the actual scheduling process. Sorry, I'm having, all right, there we go. Yeah, so like I mentioned, I'm just gonna go over the history to talk about sort of how technical decisions that were made by people before me, as well as myself, have impacted users, validators, and just sort of this feedback loop between how users are economically interacting with the chain and how we have developed banking stage or block production. Yeah, I'll also be calling it block production or banking stage. They're interchangeable. They just mean the same thing, and the nomenclature has changed over time. I started in 2022, so my knowledge of banking stage before that period is pretty limited. I tried to do a little bit of research on what it looked like before then. And I have an idea at sort of the beginning of 2022, but I didn't go further back than that because I don't think it changed too much. It was extremely simple when I first began. And then, yeah, I also wanted to just highlight on this slide sort of where, can you all see my mouse? Yes, okay. I just wanted to highlight where banking stage fits in the validator. So on the left, we have packets coming into the validator. This is some sort of networking stage QUIF is what we use now. Back in the day, it used to just be UDP. There's some networking stage here where we're receiving transactions from users or from other validators. They flow in, we do some coalescing and put these packets into batches of packets, usually around 64 packets. Those get passed off to SigVerify, which just checks the signatures of these transactions and whether those are valid or not. If they're invalid, then they just get dropped off here or marked with some flag that indicates that we shouldn't process them. Then they come into banking stage. Sorry, lost my place on my notes. Yeah, I'll get into the details on this a little bit in the next slide, but here's where we do the actual packing and block producing and scheduling. If transactions are chosen to be included in the block, they'll go off to POH, to be recorded in the POH stream. After they're successfully included in the POH stream, they'll be sent to broadcast stage, where they're eventually sent out over Turbine so that the rest of the network can receive this and validate the block. There used to be forwarding in banking stage. That was always a mistake, and it's no longer in there. So I'm just not going to talk about it anymore for the rest of this conversation. And because Solana is a parallel blockchain, this banking stage is multiple threads. And how those threads have interacted with each other has changed over time, but there's always been at least 6+. So the first implementation of banking stage was incredibly simplistic. I'll just call this first in, first out. And I'm not sure this was the original again, but this was how it was at the beginning of 2022. We had 6 independent threads, 4 for non-vote transactions. So here's the transactions that y'all are probably mostly interested in, but and then 2 threads for votes. So we have votes coming in through different paths. They submit over the TPU or over Gossip. And each of these threads just operated essentially independently. Each thread had its FIFO queue, and it would pop these packet batches off from SigVerify and just put them into its queue. And it would hold these packets for up to 8 seconds before we become leader. So before we become leader, we'll be receiving packets from users and other validators forwarding to us. And we'll hold on to those for some period because they're still valuable and they may not be included in previous blocks. We want to hold on to these until it becomes our chance to produce a block. And the way that this was originally done, we just pushed them into this FIFO queue. And then when the leader slot came, each thread would just iterate through its local queue and attempt to process those packet batches as they are. And then within each thread, I heard a ping. Is there a question?
Yeah, just a quick question in between. A little might be a little too technical for this, or I don't know if it fits here, but how should we imagine that first in first out queue? Was that a channel between the scheduler and the bank, or?
Oh, at this point, there was no scheduler. There were just independent threads. So these 4 non-vote threads have a shared crossbeam channel from SigVerify, which is also another queue. They would pop off from there and then store those packet batches in their own like thread local queue for like those 8 seconds up before leader.
All right. Yeah, we noticed that the crossbeam is really highly used in the code base all around. So it makes sense.
Yeah, it's still used pretty much everywhere.
Yeah.
Yeah, and then each of these threads would then, when it went to process these transactions, would reach into the bank and try to take account locks. If it failed to take the account locks because some other thread was touching those accounts, then this transaction would just be marked for retry later on. This is a form of optimistic concurrency. We sort of wrote these threads and they would assume that they can grab these locks, and then if they fail, they will just retry at some later point. Not quite as bad as something like some of the other scheduling algorithms you might have heard of, like block STM, where they execute the entire transaction and then throw out the result after doing all that work. We at least don't actually execute the transaction here. On the positive side, this is extremely simple. And when you've got good input, so no contention, or by contention, I mean no transactions conflict with each other, and there's no invalid transactions, this is pretty damn hard to beat in terms of efficiency. This can process a ton of packets, but that assumption that you've got good input is a huge part of that. And realistic input on mainnet does not look like this. There's always invalid transactions. Some of them, it's not really like anything that the block producer can do because it's just they got included by the previous leader. So now you can't include them. There's also just like, if there's invalid signatures being submitted, then these packet batches can be sparse. And so you have these loops where you maybe only have a few transactions in each batch that you're actually executing. And yeah, when there's interesting economic opportunities on chain, a lot of users will be trying to interact with the same state. And that means that this optimistic concurrency really breaks down. And a lot of these transactions in the batches will just be retried later on. And this encourages spam, at least how it is here, because there was no way to get to the front of the queue. It's just a FIFO queue. So my only way to be early is to just send my transaction to the leader early. And so what users would do is they would just send to the next 2, 4, 8, 12 leaders so that they could be at the front of the queue when that leader became, or sorry, when that validator became the leader. But if everyone's doing this, then I need to send out further so that I get to the front of someone's queue. And it's just a huge mess. It's totally unreliable for users. And somewhere in the development process, they decided, okay, we need some sort of fee to charge users where they can just pay more to get to the front of the queue. So this is what priority fees were intended to do. And these became active in July of 2022. And it seems like a great solution. And I'll talk about why. I think it is a good solution. I think it was implemented poorly, and I'll talk about that very soon here. But yeah, the idea is like when it's not busy, the user doesn't need to pay this. And when it gets busy, users can pay this to just get their transaction executed if they think that it's worth doing that. And the validator gets rewarded for choosing these prioritized transactions because they would earn more money. Yeah, and I'll just like highlight here that like we had a technical problem here with like the FIFO queue and contention and spam, and the solution was an economic one, introducing these priority fees. All right, so we added priority fees, but that means that we can't keep the structure that we had before. We had we were storing these packet batches as they came in basically from the network, but that doesn't make sense if each packet, or sorry, each transaction, I'll say packet and transaction are the same thing because each transaction is one packet. Each transaction had its own different priority. So we can't prioritize like each transaction batch. We need to break them up. And basically what we did, we just split up these packet batches into the individual packets and put them in a priority queue. It's amazing, so simple, and everything should just work. But it doesn't. Implemented very poorly. This is what was happening in like 2022. There's a couple of issues. One, the way that it was doing batching was extremely naive. It didn't consider the conflicts between transactions within the thread. It just pop off the top 64 transactions from the queue and attempt to process. And yeah, it's probably good to mention here. In the current Solana protocol, you cannot have conflicting transactions even in the same batch, just because of a protocol constraint. This will be removed by SIMD 83. I don't know why this was ever there in the first place. I think the idea was to make it so that validators on replay could just take these packet batches as is and execute. But as far as I can tell, we've never done that. So not sure why this was ever enforced. And beyond that, there's also still this optimistic concurrency. We still have 4 or 6 threads racing for these locks. And so if there's hot state that everybody wants to touch, then like most of those packets will end up being retried. On the positive side, it's still relatively simple and fast when there's no contention and like good input. But as soon as those break down, there's like still this incentive to spam. You can get to the front of the queue with higher priority fees, but there's still this race for locks. So I'm still going to try to spam at least to get one transaction in each of the independent threads. So like you would want one copy of your transaction in each of these 4 independent banking threads. Let's say you were the top paying transaction. If the other thread just happened to be faster, you could still lose like the auction for that state. And so people just spammed because it worked better than priority fees, which is obviously not what we intended to do. And yeah, then Solana summer happened. These NFT launches in the summer of 2022, they were insane. They would generate millions of packets per second in some cases. It led to at least one outage. I think it might have led to 2. And I wasn't working on it at this time. The TPU would just get slammed with these packets, and it would make, we had a bad networking stage at that point. It's gotten a lot better. But we'd just get starved for packets in banking stage, and banking stage itself would be extremely slow because all of these transactions that were paying the top priority conflicted with each other. And so when we popped off those 64 transactions from, let's ignore multiple threads. Let's say we only have one thread. We'd pop off 64 transactions, but they all conflict. And so only the first one would succeed to lock, and we'd just mark the next 63 as retry later. But they don't get retried immediately. We'd like execute that one transaction, and then move to the next 64 transactions in the queue and process those. Again, they're probably conflicting in these NFT cases. And then we just march down, and the only time that these like retried transactions happen is after we've looped through the entire queue. And this basically means priority fees don't work at all unless you're literally the top paying transaction. And so again, the solution to this is just, why would users bother to use this priority fee? They can just spam, and it's as effective or more effective. Yeah, at this point, we knew we needed to get proper scheduling, but it was such an issue with all these NFT launches that we needed a Band-Aid. We couldn't wait for this, a magnificent scheduler to come in. We needed something that just worked and would let us survive. So this is second half of 2022, somewhere in the summers when we started this, but many late nights spent with Tolly, Tao, and Steven coming up with some hacked emergency fix for banking stage to deal with this. And what we came up with, we just ended up calling it a thread local multi-iterator. Basically, the biggest issue with the previous approach, what I called spray and pray, was that non-immediate retry. We'd grab those 64 transactions, and 63 of them would basically not execute for some time. And instead of naively grabbing those, we just have 64 iterators. Someone has a comment.
Berg having some PTSD.
Yeah.
Just having some flashback from those times when
and it was not a good time.
Again. Yeah.
But yeah, I'll just describe the thread local multi-iterator approach real quick. Instead of naively grabbing the top 64 transactions from the queue, we would create 64 iterators. And we begin the process by just placing the first iterator at index 0, which would just, that transaction would always be selected. And then the next iterator would begin at the previous iterator's position +1. So in that case, be the second one. And then we would march forward until we found a transaction that didn't conflict with any of the transactions that were currently in the batch. And then we just do that loop until we get 64 transactions for our batch, or we hit the end of our transaction queue. This basically meant that each of our batches of transaction, now we knew that they didn't have conflicting transactions within them. So we could, the only thing that we had to worry about now was just the race between different threads, which, there's only 4 of them. Only so many conflicts are going to happen. One of them will win, but it was significantly better, especially for these NFT launches. So like I said, like previously we'd have basically, a batch of 64 transactions, but 63 of them would not actually execute and they'd just be skipped and retried later. Now we'd skip over those 63, and instead of being delayed until we get through our entire queue of transactions, the second of those 60, or the second of those top 64 would just be in the next batch. So it's much more immediate retry. And it did what we wanted. That's about all the positive thing I can say about it. I hated this approach. We finally just deleted it from master, but it did its job. It held shit together with this hacky solution until we got a real scheduler that finally eliminated like the optimistic concurrency and made priority fees a lot more reliable. Negative side, yeah, complex, slow, tons of edge cases that led to priority fees not really being respected. And we still have this multiple threads. So your users were still encouraged to spam quite a lot. Not as much as they were before, but it was not solving the spam issue at all. This went live somewhere in the second half of 2022. I kind of forget exactly when, somewhere before breakpoint. And I don't know if you all remember the end of 2022, but there were some things that went on and we entered a bear market, which was actually kind of good. This hacked solution was not robust. And it was just meant to get us through, and the bear market helped us a little bit here. With the bear market came a significantly reduced on-chain activity, which meant that this thing was not as critical, and we basically had a lot more time to stop throwing together these scrambled together solutions and come up with a real solution. All right, so that brings us to what we call the central scheduler. And instead of having these 4 independent banking threads, we would have now 5 threads. So we've got 4 workers and 1 scheduler thread. And the scheduling thread, probably should be called packing and scheduling, but it's called scheduling. Hindsight's 2020. It'd handle all of the priority ordering, and then it would just send batches of transactions to be processed by the workers. And it would do this in a way that made sure that there are no more account conflicts between these 4 worker threads. Implementation-wise, this is a bit complicated, but the description of it is fairly simple. We have a priority queue that we pop transactions off of, and then we build a directed dependency graph here on some subset of the queue. These edges, each node in this graph is a transaction, and the edges indicate some sort of conflict. So like these cannot be executed in parallel. They'd have to go into like separate batches or be executed on in serial. Once this graph is built up to some size, I think it was like about 1,000 transactions, we basically select transactions from this left, so no incoming edges, and those are the transactions that we can schedule now. So these 4 in this example could just be scheduled to separate threads, and then they would be popped off of the graph, and we move on to the next series. So like this one could not be scheduled now because it might conflict with, if these 2 got scheduled to different threads, this one can't be scheduled until at least one of those completes. These 2 could be scheduled in parallel because they don't conflict with each other, but since they both conflict with this one and this one is not completed yet, they have to be scheduled, in serial behind this guy. Yeah, and then once you schedule some number of batches, and then if you have more transactions in your priority queue, you just pop them, add them to the end of this graph, and you keep going through, and it gives you a pretty reliable way of respecting priority fees. There's no more account lock failures. So we don't have to worry about this race between the threads. Massively cut down on the reasons of spam. There's no more of this multi-thread bullshit where you can just send and like hope that you can, your thread beats the other threads. The scheduler has a view of all of the received transactions, and it always just operates in priority order for conflicting transactions. So this made priority fees way more reliable. And at this point, when this is finally introduced, it was more reliable to just pay the fee than it was to send 30 transactions. Downside, it's fairly complicated. It was slow in some cases, and because of our rush in the past, there was also some issues with how we prioritized. And so I'm going to do a quick aside, stop talking about scheduling. We're going to look at how priority fees work, because when we launched this, we said something's not quite right. You know, we're seeing all these transactions come in, but a lot of simple transfers that don't have these priority fees attached, they're not landing. Why aren't they landing? And this comes down to how we ended up doing the extremely simple prioritization in that spray and pray method that I mentioned previously. The users set a compute unit price using the compute budget program, and this is what determines the prioritization fee. So you just take this compute unit price, which is specified in micro lamp ports per CU, and then multiply it by the compute unit limit. This limit is either coming from another compute budget instruction or some default value of 200,000 per instruction. And when this was first introduced, the way that we did prioritization was just simply based off of this number specified here. And this means that if we have a simple transfer that doesn't have a priority fee attached, the priority is effectively 0. And something like, let's say, a 1.4 million, which is the max compute unit transaction, just attached some extremely small value here, let's say 1, that would be always prioritized above our simple transfer. And it's totally wrong, because I'm, as leader, I'm selling 1.4 million CUs to this guy for basically 1 additional LAN port, when I could have sold it to a simple transfer for a way more price effective way. The other issue is this compute unit limit is not the only cost towards our block limits, which is what leaders care about. So we've got 48 million CUs per block. I guess it's 50 now. At the time, it was 48 million. And this compute unit limit was the majority of that, but not all of it. It accounts for the execution of instructions. So simple transfers, it's like 150 CUs. And then something like a user transaction is just whatever that program happens to use. But there are other costs that count towards the block limits, such as signature costs. So each signature costs, I just grabbed the code picture here, but it turned out to be 720 CUs. So if you had an otherwise equivalent transaction, let's just say a simple transfer, and one had 1 signature and the other had 2, it's pretty close to double the cost towards block limits, but they both have the same priority, which would just be the CU price. Yeah, this is just totally broken. It's not good for validators because it's losing them money, and it's not really good for users because simple shit isn't getting through, and more complicated transactions that shouldn't be are the ones that are actually landing on chain. All right, to do better, we just have to look at it in a different way. As a leader, I'm selling block space. I've got 48 million CUs to sell. I should just sell to whoever is willing to pay the most per unit. It can be optimized a little bit. At the same price, you'd probably prefer to use a larger transaction so you can just sell more and get a higher overall reward. But realistically, you just want to sell to whoever is willing to pay the most per price. And stepping away from blockchain, I think this makes a lot of sense. If I'm selling apples, you just sell to the person who's paying the most per apple. Very obvious, but that's not what we were doing before. So yeah, instead of that CU price, just prioritize by the reward divided by the cost. So the reward is basically the fees that you earn as the validator, as the leader, for including this transaction, and then the cost is just how many CUs does this count towards the block limits. It's not quite perfect because we don't actually know how many CUs it'll take to execute ahead of time. We have to rely on the user's requested CUs or an estimate. But the incentives are kind of right. If you request exactly what you use, you basically get higher priority for free. And if you use the default limit, you basically just have to pay more to get the same priority. There's also this +1. I'll mention that real quick. Mainly it's there just to avoid having to worry about dividing by 0. But this also has another benefit, which sort of kills 2 birds with 1 stone, which is what I mentioned before. If we've got 2 transactions, one is buying 200K CUs for half a Lamport per CU, and another that's buying 2 compute units for the same price, I'd rather sell the guy buying more. And this just makes that happen, even if it's like a very small fudge factor. And so now this basically means that these simple transfer transactions that a lot of users are sending no longer really need these compute unit fees. And I'll step through an example here. I don't have it written on my slide, unfortunately. A simple transfer costs roughly 1,000 CUs. If it has no priority fee, the reward to the validator is still 2,500 Lamports, just from the signature fee. And so this roughly maps to 2.5 Lamports per CU. And if we compare that to a user transaction using the default limit of 200K, and they've got a CU price of 10 micro Lamports per CU, that's only 1 additional Lamport in my reward. So my reward is 2,501 Lamports, but I've sold 200K. So the price per Lamport overall is like 0.01, really low. And yeah, to be equivalent to the simple transfer in this new reward over cost model, it'd have to have near 2.5 Lamports per CU as the CU price. So now using this, it's way more cost effective for validators because they will be choosing the transactions that earn them the most for their block space. Finally, back to scheduling. Talking about something that's modern. The Priograph scheduler was doing all right, filling blocks under many circumstances, under normal conditions. But once we got to heavy load, it would struggle, and we'd see blocks not full, which is right when we needed them to be full most. So it's really shitty. And this is largely one because of like some bad looping logic, but sort of just a design flaw. We rebuild this graph every time we begin our iteration process, and that's expensive. Caching it and like updating the graph incrementally is like a lot more complex. This is what the unified scheduler does, and we have plans to port that to we have plans to port that to block production. But somewhere along the line, I was like, let's just come up with a much simpler model for block production scheduling and try to do something very simple, but just faster. So coincidentally, on New Year's Eve of 2024, so pretty recently, I just wrote an extremely simple scheduler that I called the greedy scheduler, and it just scheduled whatever it could when it could. No more graph building. We just pop off the top priority transaction, check the locks against the batches that we're currently building for SIMD83, check that the locks don't conflict with multiple threads, and then do some load balancing between the threads. And yeah, we tried this, and it was actually too fast, oddly enough to say. What was happening when we first started testing this is as soon as our 4-slot leader allocation, whatever we call it, you get 4 slots as leader. As soon as that would begin, we would queue up so many transactions in the scheduling that we just filled all 4 blocks right at the beginning. And that's not good because while you're leader, you're also still receiving transactions. And a lot of those might pay more than what you had in your queue when you began being leader. We just added some throttling in so we don't immediately fill, and that gives us a chance to receive transactions while we're going. And this is a pretty simple way to do it, but we just said, don't schedule more than 25% of the block at any given time. So like, by that I mean don't have 25% or 12 million CUs outstanding or like in-flight transactions at any given time. It's been working well so far, but there's no ideal packing or scheduling algorithm. Different operators have different goals. They're all trying to make money, but they have different willingnesses to do different strategies. Some might even do malicious things like sandwiching their users. Obviously, we're not going to do that, even if it is the optimal strategy. There's also just some stuff that we know as Anza, like that would be extremely profitable or much more profitable than the default behavior. But we view it as like a bad default because it might do stuff like king making certain apps on chain or just negatively impacting users. And as the default client writers, we need to balance sort of how we view validator operators and then fairness to users. And what this basically I'm trying to get to is different operators basically want to modify this behavior and not pack quite the same way that we do, or that what our default does. And right now, the only way to do that is for them to fork our client. And this sucks for a number of reasons. It sucks for a number of reasons. Mainly, it's burdensome for operators. They need to maintain some fork. Obviously, they can just use Jito, but a lot of people modify Jito as well. They need to, every time we change something, they just have to rebase or update their stuff with, because we're a moving target. That's often complex. It breaks, leads to security issues because they do something wrong. Whole bunch of consequences here. And I'll get into, I already kind of said all of this, so I'll just move on to the next slide. Because I need to talk about the elephant in the room, Jito. Jito launched at the end of 2022. It is a fork of Solana, and they launched somewhere in the transition from the spray and pray method to thread local multi-iterator. And I'll just emphasize, at this point in history, the scheduler did not exist. And so the approach that they went with was they just spawned this additional thread in banking stage that used a similar optimistic concurrency model as what existed at that time in Solana. This additional thread is to process bundles. I'm sure you guys have probably heard of bundles, but bundles are just a primitive that offer atomic execution of multiple transactions. If any of the transactions fail, then none of them will be included in the block. And they come with a Jito tip that goes to the leader and is split between the leader and I think it's either the Jito Foundation or Jito Labs. I forget what their company structure is, but they get some cut of that fee as well. The bundles are simulated by the Jito block engine. And so when the validator or the leader receives these bundles, they are bundles that Jito has basically said, these will succeed or have a high likelihood of succeeding. And so Jito wants them to go at the top of the block, because if other stuff gets scheduled before them, they're executed before them, they are much less likely to execute successfully. And what that means is when they implemented this, they gave priority, or basically when it comes to that locking phase where each of the threads are trying to optimistically lock the accounts, the Jito bundle thread gets priority over the worker threads in the scheduler now. And this kind of sucks. We're back to what we had identified as an initial problem of this race for locks. And this is again back to a world where it's making priority fees less reliable. And because the Jito bundles get priority, it makes Jito tips, even for single transactions where you don't really need a bundle, it's still beneficial for users to send through that path because they get the priority, so it's more reliable. And this is a huge positive feedback loop because operators use Jito to get more income from the Jito tips. This makes priority fees not work as well. This makes real users realize that Jito tips work better than priority fees, so they're more likely to use Jito. And this makes operators want to use Jito more because everyone's using Jito. So they kind of have to use the Jito fork, otherwise they won't get half of the user transaction flow. And this is a difficult moat to break. And again, I want to be clear that I'm not trying to throw shade at the Jito team. I generally think that they are aware of this position in the ecosystem, and we have been working with them, though I can't really mention any specifics here, but we've been working with them on like how to address this and sort of do what is best for the ecosystem and make this not as bad and not as sort of split for users, because it kind of sucks from a UX perspective as well, because users now have to be aware of these sort of infrastructure things like Jito tips and priority fees, and how do I know which one is best at this time? There are also other forks besides just Jito. Jito is just the biggest, and they have something like 80% of the stake on the network today. But all of these forks have complicated changes. And with Agave changing so much, it's pretty difficult for these small teams who mainly focus on other things. They don't have a huge focus on the validator fork. They're mainly interested in stuff like the block engine. And what this leads to is mistakes creep in when they're updating to newer versions of Agave. And this leads to security issues. We've had several scares over the past year. How does the greedy scheduler? It's pretty similar to FireDancer's approach. Yeah, I haven't looked exactly, but both of us basically, I think that they use the same prioritization model as we do, just reward over cost, because it's sort of what inherently makes sense. But yeah, they just, as far as I can tell, schedule what can be scheduled. It's extremely similar, though, like the way that we implement it is slightly different. Yeah, and because of these scares, I wanted to talk a little bit about the future rather than focusing on the greedy scheduler, though we can get back to the greedy scheduler in a little bit. Yeah, so as I mentioned, there's like these huge security risks that come with forks, teams maintaining their forks of Agave. And we don't really have a problem with people trying to modify the packing logic like they want to. What we have an issue with is just these security issues. And so we're beginning on this new project that we're calling scheduler bindings that we're hoping will maintain safety and the security of the network by checking the validity, but give operators basically total freedom in producing their blocks how they want to. Another aspect of this is just priority fees have become way more common over the past year and a half, and validator competition over block rewards has started to increase. People used to not care because inflation was so high relative to block rewards, but I just picked a random validator that was doing reasonably well. Priority fees are pretty high now, and that's where a lot of the money as an operator can come from. And so, teams are realizing this and starting to fork the client so that they can make more money than their competitors. And obviously you can't make more money if you're just running stock Agave with the same logic that everyone else is using. So they sort of are forced, if they want to compete, to fork. And so this is another aspect. We want to just lower the barrier to entry of like forking and maintaining a fork, and just make it as easy as possible for operators. And basically the idea is that we will enable you to have an external packing process. So now we have two separate processes. We've got the validator itself and then a packer. And this packer is just your custom packing logic as an operator. And how we envision it, there's a few ways, but basically if you're running that packing process on the same box, you can just have your TPU, signature verify the transactions and then pass them off to this process. It will choose which transactions it wants to land in the block using whatever logic you want, and then it feeds it back into an internal scheduler in Agave that does all of the checks. Make sure that you're not going over block limits. Make sure that you're not violating the protocol somehow. Giving feedback to this packing process to say, hey, here's how many CUs you used, here's how many you have left, here's how far we are through the block, all the information you need to pack. And then those transactions just get scheduled, and the most efficient way that we can do. And again, scheduling is easy. It's the packing part that's harder. Once we have, this process choosing the transactions for us, it's pretty easy on the Agave side to just execute them in a safe way that is efficient. And yeah, we envision this will be used in other ways. Like you could run this on a separate server where instead of having it run, just accept packets from your TPU, the validator can redirect packets to this process that's running on an external server. Maybe they're building for multiple validators and they're receiving transactions from all of them. It could have an extra port open that accepts bundles and merges them in however it sees fit. A priority port, such as Paladin. And all of this fits in, and it goes through the same interface. We have to make some changes in an Agave to enable the features that these builders want. But the idea is just try to give them as much freedom as possible, and we will try to, maintain what we're good at, which is safety and correctness. But we want to leave the competition up to people. And the reason why I'm sort of talking about this here, I think, Jeff, like a lot of this group is like how you guys can contribute to the ecosystem. And instead of talking about the greedy scheduler, I think that, moving forward, this is sort of where people can contribute more, is building these custom packers or packing logic things, because this is where a lot of the competition for operators will come from. I
love that. And I always ask, how can we contribute? And you hit the nail on the head. I'm glad Berg has his camera on, because I love watching his response to all this, because I know his brain is going. This is great. It's all I just wrote in our team chat. It's kind of if you can't beat them, join them, but make sure it's safe and secure what they're doing. And instead of letting people, I'm going to use a crazy analogy here. It's like the legalization of marijuana, right? It's like, why fight against people and let them do things illegally and dangerous and have a lot of crime around it? Legalize it and make sure it's safe and secure. And it feels like there's a little bit of that mindset here. Like, look, they're going to do it either way. Let's make it safe for them to do it for all the users and for the protocol itself. I really do love this. Yeah, Bird.
Yeah, actually, it's a good point, because I was thinking on this. I wanted to ask Andrew, what do you feel? I mean, I do have the impression from the tone and how you talk about these things that it's, besides that, it's kind of inevitable that people gonna, try to tune the code for their own advantage. But how do you feel about people that are actually changing the code on the way that risks the security of the chain from those changes? So, for example, I think Brian can talk about it a little better, but I remember that when 2.1.1 was released, a bunch of the validators crashed because what you just said, Andrew, that they are focusing on other things, and they were not focusing on, or I don't know if they were focusing on, but it actually happened that some of the validators crashed after the Argv update. So I know that it's inevitable, and I understand that, of course, you want to make it possible for everybody to adjust their code and make it as profitable as possible. But just wanted to have your I don't know if you can say that, the personal opinion about these changes. Would it make sense to, I don't know. Yeah, so we did a huge research a little while back,
Yeah.
and I think Jeff going to talk about it also in Accelerate. Just wanted to know what you're feeling about this. What you're feeling about changing a lot of things in the validator code and actually probably causing problems.
I mostly keep myself in block production land, where a lot of the changes are about efficiency, and most of those are not like malicious or like security risks. It's mostly just bugs that creep in. But yeah, I know there are other sections of the code that people modify that have a negative impact on the network. Voting mods are a pretty obvious one. This doesn't solve that in any way, so people are still going to fork. But I think Ashwin and like people in the voting team are looking at ways to discourage that or make it less encouraged to do that. But yeah, I obviously don't like things that make the network more risky. Outages are, it's a huge economic risk. And if you're a validator, then like you do not want to cause a network outage. And I think that focusing on safety and security is more valuable than whatever small profit that you can eke out from like these changes, compared to how much it's going to tank if you fuck up and take down the network. But yeah, well, like I said, I with this scheduler binding stuff, we're really trying to focus on giving as much freedom, but Agave still maintains like all of the protocol constraints. So we'll still be validating all of the constraints that have to produce an invalid block. And as long as you haven't modified the validator and you're just using this, external packing as we've written it, then it won't produce an invalid block. And that's like a huge focus here.
I think that's kind of a common theme in actually in the whole code base, that everybody's trying to make it a little more modular. That I guess you can hold the important parts in your hand, but in the same time you can give them freedom of the validators to just swap out parts without actually getting deep into the code. Yeah. So I think I see the common theme in this part.
Oh yeah, I'll also mention like with this being an external process instead of just like a thread within the validator, like a plugin or something. One of the things we want to enable is like you can swap out the packing logic at runtime. So you can just change your packing logic without restarting your whole validator. And this is huge because it lets operators like innovate without needing to take an hour to restart every time. They can go every few minutes and change their packing algorithm and do exactly what they want. It looks like Brian might have a question.
Yeah, I'm just kind of smiling a little bit. The game of whack-a-mole against sandwiching goes on. Because just when we think that between some stuff that Jito's doing and some stuff that we're even doing at Triton to kind of help with that, just when we think we're at a point where we will have sandwiching under control, we're now going to like push block packing out, potentially let third parties do it, and of course they have the incentive to start reordering for sandwiching again. And I'm not saying you shouldn't do what you're doing, because it does make sense, but the game of whack-a-mole continues, so we'll have to think about that in that new world. So
yeah, 100%. I think this that it's not a purely positive change. There are negative impacts. Like there are validators who are willing to do sandwiching. I think most aren't, because it's negative UX. It makes users less likely to want to send transactions, which don't know if I'm allowed to say anything about the value of Sol, but you can imagine that's not a positive impact. So I don't know how many are willing to do that, and there are certainly ways like a lot of the transaction sending services can blacklist people that they view operators that they view as doing this more often than others.
Yeah, exactly. And that's the piece that we're working on and contributing. That actually hits mainnet on Monday. It hits production on Monday. So that's the part we're working on. But anyway, I just I don't want to derail your conversation. Great presentation so far. But and I look forward to the continued game of whack-a-mole. So.
Yeah,
and what keeps it fun.
Yeah, and this is what we know. People are gonna try to make money. People are going to try to get an advantage. In the validator, people are going to try to attract more stake because they can show more rewards, and they're going to do what they have to do. Some of those people are competent developers that could do it in a way that is likely not damaging. Other people aren't. And it's that latter group. Actually, it's the whole group that's problematic, but it is inevitable. And I really do like the idea that, you know what, we're not going to fight some of this anymore. We're going to let them try, and then we're going to make sure whatever they send back in is safe and secure and not going to blow the thing up. I think there's a lot of, that is giving people a little bit of rope to try to build their business and use their own, strategy and acumen. But look, like Brian said, it's all a moving target. And that's kind of what makes it fun. So, Berg?
Just one more quick thought on it, and then I will let you go further. What just Brian said, sandwiching, that also brings up the possibility of censoring certain people if we, let third parties back the blocks and take a look at stuff. But yeah, just a quick thought on that.
Yeah, that's the next one. The censoring stuff.
100%, you can do that, but if you wanted to do that, you could do it today by just forking the client, and anybody who is sufficiently motivated will. And back to Jeff's point, I don't think it's just incompetent people who are making the mistakes. Like I said, I don't think the Jito team is incompetent by any measure. We're changing so much in Agave. It's really fucking hard to maintain a fork that doesn't screw things up. Because we move things, and we have some level of communication with the Jito teams, like, hey, we changed this, make sure that you didn't, break it in your update. But as there are more and more of these teams, I can't reach out to 100 teams on every change that I make and say, hey, make sure that you didn't break this. So this is really a way of dealing with what we view as inevitable. People are going to fork the client. They already are, and it's ramping up. There are increasingly more every week. And yeah, it's just to try to maintain some level of safety in doing so. And also, yeah, I mean, I mentioned earlier, you can hot swap out like the Packer at runtime, and like that's also just beneficial for Anza's default scheduler, because now I can iterate a lot more quickly than I could have in the past. I don't need to wait 2 hours in between changes. So
awesome, Andrew. Thank you so much. This is insane. Like, it's like we've been, Brian's over there smiling because, Brian gets to come in at the end of this program and really try to tie all this stuff together, between what we learned with Magic Block and then Max and now you. And actually, I'm going to let a little cat out of the bag. Folks in the room, questions, comments, thoughts. Let's open it up here for a few.
Yeah. Hey, Andrew. Thanks for coming in. I was wondering if you could take some time to talk a little bit about the pyrograph scheduler. I know that was like that old news, like you said. One thing I was really interested in is how the scheduler uses like a transaction state to, I don't know if this is still current implementation, I think it is, to track unprocessed and processed transactions. And like you said, we don't use the forwarder anymore to forward process transactions. So everything just goes through the broadcast stage. I was wondering if you could just like discuss just talk a little bit about the logic there, using the transaction state to track processed and unprocessed transactions before you actually broadcast them into Turbine.
Yeah, I mean, so in the scheduling thread, we have like two structures. We just tie them together and call it a container, but we've got like the priority queue and then a map that like actually holds the transaction values or the transaction states. When we pop stuff off of the priority queue, it's no longer in that queue, so we won't pop it again. And if it gets scheduled, then we like mark in that map that it is an in-flight transaction. It goes off to the worker thread, which will then try to execute it. If it executes it successfully, it gets broadcast out right after being included in the POH. Then the result gets committed to accounts database. And then the worker thread will send a message back to the scheduler, which says like, hey, I'm done with these accounts. And then at that point, if it was like successful or failure, like the transaction got included, that transaction state gets removed from the map. If it was something like it hit block limits or it failed to record because the slot ended while we were processing, then it can get retried, and we just basically insert that ID back into the queue again. Is that what you're asking? I'm not sure.
Yeah, so sort of in line, but what I was actually asking was, when I compare your implementation of the transaction state about 6 months ago with your current implementation, a lot of things have changed. So you can see in the transaction state, previously you were using the sanitized transaction. So you had a sanitized transaction come in, and you process this through like you have this sort of enums, right? Where you have the process, the pending state, and all of that. I'm sure you're familiar with that. But recently, your recent implementation of the transaction state now has to do with some sort of option, right? So you're not actually passing this sanitized transaction into this transaction state anymore. So you're using like a sort of option where like the transaction is available for scheduling if it's a sum, and it's currently being scheduled or processed if it's a none, that is if the transaction state doesn't hold any transaction. I was trying to understand the design decision behind that implementation. Why you stopped passing in sanitized transactions and the hash of the sanitized transaction message, and just decided to use the option instead. Does that have anything to do with the pyrograph?
No, it didn't really. It was just a refactor. There were only like two useful variants in that enum. There was like unprocessed. I forget what the names were. It was like unprocessed or like a bit in flight, somewhere along those lines. And it was equivalent to just having an option, so I just simplified it, and it just reduced how much code there was. The sanitized transaction change was a performance thing. So we have these SDK types which have like a bunch of internal vectors of vectors, and they're really bad for performance because each of those vectors is like a unique allocation. And every time you do an allocation, you have a chance of like your local allocator cache not having the memory to give you. And if it doesn't, then it has to grab like a global lock. It can take milliseconds to do that. And when we're trying to ingest thousands, hundreds of thousands of transactions, into the banking stage, doing all of these allocations can be really expensive. So we sort of made the transaction type, the transaction structure generic. And what we're moving towards is a zero copy or like non-deserializing view of the transaction. So rather than doing like this bin code deserialization that can do, I think in the worst case, it's like 700 allocations. It's insane. Now we don't do any allocations, and we just scan through the actual packet, the actual bytes of the transaction, cast some useful offsets of like where are the instructions, where are the signatures, where are the pub keys, blah, 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 blah. All the things that we need to access the information that people need from the transactions, or by people, I mean we, for like executing the transactions. And this way we can just avoid the overhead of allocating, which the issue with the allocator is that the allocators are really good at dealing with consistent memory allocations, but it's not consistent if you are for 3 hours not receiving any transactions, and then all of a sudden you're receiving 1 million in 1 second. And that's basically what happens when we're a leader. And it just totally fucks these allocators, and the rate at which we can ingest transactions into the scheduler drops. And that just means that we don't have like a complete view of all of the transactions that we want to schedule that are like in the pipeline from SigVerify. And we just do a worse job at packing. And so this was just a way to speed that up and make it so we can ingest more transactions. And like in some cases, it's ridiculous. It's like 60 times faster. Not in all cases, but it is much, much faster to do this view approach. Yeah, it's just like a performance optimization, so we can pack better.
Awesome. Thanks for clarifying that, because I was like, why would I was kind of wondering the design.
Yeah.
What was the philosophy behind the design? Speaking of which, the future implementation where clients would be allowed to have their own custom packets. I believe that's what you mentioned for future implementation. Correct me if I'm wrong. There'll be clients will be able to batch the transactions. Like they'll be able to implement their own mechanism for batching transactions. Was that what you actually?
Yeah, there will be some mechanism for them to batch transactions together, but only in certain like circumstances. In many cases, they don't care about like the actual batching. They will just care about, I want these transactions to go in, and then Agave can parallelize that however we want. But yeah, in some cases for something like a bundle, we would need to provide some way for them to say, I want these 3 transactions to go together and not go in if any of them fail. So sort of what we have in mind here is some set of like execution flags just indicating, here's how these transactions should be processed in some special way. And if you don't use them, that's fine. But we probably won't use them in like our reference implementation because we don't do bundles or anything.
Awesome.
Yeah, we just want to provide the freedom for people to do what they want, but with like the safety of this interface.
Yeah, that would be really cool.
Quick question. You were talking about that it will be kind of swappable to have that packing logic swapped. Would you be able to give us some pointers where to look in the code base? Because it's undeniable, like we have a whole bunch of lines of code and a whole bunch. I think it's getting more and more now that the thing is getting more modularized. Could you give us some folder that we should look at to look at the logic and try to think on implementing it in a different way? Or which part should
not
be?
yet, because this interface does not exist, and we're still like designing it, and we have not like announced it. Like the closest thing would probably be something like the greedy scheduler, before you get to the thread selection part. But something like that is what like a packer could look like.
Mm-hmm.
So that would be in core source banking stage transaction scheduler and then greedy scheduler.rs.
Okay, cool. Thanks.
So Andrew, thank you.
Of course.
Was incredible, very enlightening, and very exciting for us to be able to put our mind to some of what you shared as far as what we can be doing on our end as we look over the next, few weeks of things that we could do in class. Awesome. Cool. Well, everybody, thank you so much. We'll see you on the flip side, and, ping us if you need us.